Okay, so there it goes. So we are recording. Okay, so heads up, you are being recorded. Although the range of the microphone is not very much, so little whispered discussions are almost certainly not being recorded. But if you do ask a question, of course you got to say it loud enough for me to hear it, and at that point it's possible it might be being picked up on the recording. These recordings, of course, are going to go onto my YouTube channel as a very convenient means of me, distributing these recordings to y'all, right? So anyway, if you ask a question, you might be on YouTube. Yes?
Will you be essentially repeating the questions for the benefit of the recording?
Maybe depending. So the question was, will I be repeating the questions for the benefit of the recording? And so sometimes, when I think about it, I will. Yeah. It's a good point. Yeah. Okay. So let's talk about quizzes very quickly. Quizzes at this point no longer have any mathematical content. The quiz question is just now a kind of a little hack method for me to check attendance. Right? So the quizzes will still be on Sakai. So you can still access the quiz from anywhere, right? But as usual, the answer to the question can only be determined if you're physically in the room. So there's going to be a number on the board every day. There it is. Is that legible? Okay, let me darken that up a little bit. Is that legible? No. No? Still no? Okay. All right. Okay, so the number is 123 today. 123. Easy number to remember. So you just have to type in that number into the quiz. By the way, the quiz is now going to be available during all of lecture. This is not a 5-minute time situation because it's mathematical content kind of a deal. I just want to make sure that you're here at some point. You can be late. Fine, doesn't matter, right? You can leave early, it's fine, whatever. Y'all have busy schedules. I get it. So anyway, at some point you need to be physically in the room, see the number, type it into the quiz on Sakai, and you'll get credit. If you're not sure if you typed it in correctly, do it again. I have it set up now so that you can attempt the quiz multiple times. If any of your attempts are correct, you will get the point, right? So it's set to record whatever your highest score is on this 1-point quiz. Yeah.
It also grades it instantly, so you can see if you guys are.
Right, that's right. You can look into the grade book and see if you have the point. That's right. Yes?
How quickly will the live lectures be uploaded?
As soon as I get back to my office and remember, I will upload them into the YouTube. Yeah. So, by the way, standing rule: if I have forgotten to upload the lecture onto the YouTube channel, I welcome reminders. Right. So if you want to just send me an email and say, "Hey, wanted to check something in the video, you haven't uploaded it yet," it's my fault for forgetting, and I deserve whatever deluge of emails I get and reminders. Much appreciated. So feel free to remind me. Okay, so sometime during the lecture, make sure to do the quiz. Right? Again, today the answer is 123. I can say the answer to the question on the recording because the quiz is going to disappear before the YouTube lecture appears. So no possibility of risk there. Yeah. Okay, does anybody have any questions about procedures and that kind of thing going here forward? Everybody on board? Okay. One other thing. So the quiz question. Some of you I know like to get a jump on things and maybe get that quiz done before the lecture starts. So I will have the quiz appear on Sakai 5 minutes before class starts. I will also, for those of you who procrastinate and do things at the very last possible second, once lecture is over, you still have 5 minutes. So it's open at 1:35 every day, and it closes at 2:35 every day. At 2:35, it's over. So make sure you do the quiz sometime in that, in that 60 minutes. Okay. All right. So let's go to one old exam question. This is from 14-15 fall, exam 2, question 5. Here's the question to solve that differential equation. So this, of course, is a lot like the differential equations that we were looking at in today's pre-lecture. It comes up, as you'll recall, from looking at a particular mass on a spring question, where you add in a friction term, right, to the situation where you have an external, a sinusoidal external force driving the system. Okay, so the idea is that if you can solve this associated complex equation, right, then looking at real and imaginary parts, you can solve the associated real equation. Okay, all right, so we're looking at this complex equation. At this point, once you write it down like this, it's really kind of a section 4.3. This is an undetermined coefficients kind of a situation. So we make a guess, which is to take our right-hand side and insert a fudge factor. Right? We speculate some multiple of the right-hand side. Okay. Now, so you say, what about the unfortunate coincidence, right? Isn't it possible that maybe our magic number is the root of our characteristic polynomial? Shouldn't we check that? Okay, sure. Let's check that. The roots of the characteristic polynomial, as you recall, are minus b plus or minus blah, 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 right? All over 2a. This real part, notice, is not 0. Right, so both of the roots of the characteristic polynomial, because b is not 0, both of the roots have a non-zero real portion. On the other hand, let's look at this right-hand side, which is 7 cosine of 2t plus 7I sine of 2t. Looking at this right-hand side, our magic number, right, there's no exponential in here. There's a 2, and so our magic number is 2i, whose real portion is 0. So the roots have a real portion that's not 0. The magic number has a real portion that is 0. There cannot be any unfortunate coincidence. Everybody on board so far? Okay, so we make the naive guess. The naive guess, very plausible, is that we're going to have some multiple of our right-hand side. You take your guess, plug it into your equation. You got to take a couple of derivatives. Right? The derivatives aren't that bad. I mean, this is just an exponential. Sure, there's a little bit of complex arithmetic, but that's not that bad either. So pretty straightforward process of plugging it in. And out comes this equation. Solve for t. There's your t. That's your fudge factor. And then from that, you can write down what the solution is. So our solution, right, we take that fudge factor. Okay, fine. So this 7 times the fudge factor is that. Everybody on board? We're just plugging in. And now how do we simplify this expression here? There's something awkward about this expression. It's a product of two complex numbers. What's awkward about it is that the first complex factor is in rectangular form. And the second complex factor is in polar form. Right? So how do you multiply two numbers that are in different forms? Well, it's really convenient to multiply two numbers that are both in polar form, and it's not that bad to multiply two numbers that are both in rectangular form. But in a sort of mixed situation, it's not convenient to do it. So our two options: I can try to turn this into polar form, and honestly, that would be these aren't convenient values. The angle involved would be a weird number. That's not very convenient. But turning this into rectangular form is easy. right? So we turn that into rectangular form, and now I can very conveniently just multiply rectangular complex times rectangular complex. The real portion is real times real, and then I have imaginary times imaginary. Both of those give me real terms. Don't forget the I squared is -1. Right? That's why this minus sign here disappears. And then real times imaginary gives me imaginary. And imaginary times real gives me imaginary. So it's a straight up FOIL. And there you go. There's your solution to our differential equation. There. Everybody happy? Yeah. Mm-hmm. Oh, yeah. Okay, so the question is, how did I get from there to there? Is that right? Yeah. Okay. Yeah, so this is, we're using a trick in complex arithmetic, which is that if you want to divide by a complex number, then you just multiply that resulting fraction by 1 in the form of conjugate divided by conjugate. That's right. So this is hidden inside of here is -5 minus 2i over -5 minus 2i. And there's your numerator, and that ends up being. Yeah. Good question. Anybody else? Yep.
Is there a reason that you guessed t times 7
That's a lovely question. So the question is, let me go back up to here. So why did I leave in this factor of 7? Right? Yeah. It does not make any difference in this case. I was following the convention of how we do this when we're interested in computing gain and phase shift. If you want to compute, if ultimately you're doing this so that you can study an actual oscillating system and you want to know the gain and the phase shift, this little trick of leaving in the 7 or whatever scalar might be there and making your fudge factor something that is explicitly being multiplied by your existing right-hand side, that's what allows you to deduce that the magnitude of that number is the gain, right? So this is necessary. You got to leave that 7 in there if you want for this to be true. In this case, I wasn't computing gain. So in this case, it does not matter at all. And if I had ignored this trick, I would have gotten the exact same answer, no problem. Great question. Anybody else? Okay. All right, so second half of this question, we found the solutions, the particular solution to that differential equation. Second half gives us 2 more differential equations. There's that one and there's this one. Oh, gosh, okay, well, look, the brute force way to answer these questions is to say, well, let's take them one at a time. This one, well, this is a section 4.3 type differential equation. I've got a right-hand side, check for roots, no coincidence. Make your guess. Your guess is going to involve sines and cosines. You'll have 2 terms in your guess for u. Plug it in, multiply it out. You get a little 2x2 system of equations, solve the system of equations, that whole 4.3 thing. Having done that, you can do the same thing here and say, yikes, look at it again. There's another right-hand side that is trig, and so no unfortunate coincidence. 2 terms in your guess, plug it in, collect terms, 2x2 system of equations, right? The whole 4.3 thing. So there's a lot of details in there, and you can do that. The much more convenient, strongly encouraged alternative is to just observe that these 2 equations are exactly the real and imaginary parts of that equation. Right? Well, and so since these 2 equations are the real and imaginary parts of that, just take that solution, that z, the real part of z is the solution to the corresponding real equation, and the imaginary part of that z is the solution to this imaginary equation. And so that's what I did right here. This u is the real part of the above z, right? And this v is the imaginary part of the above z. Much more convenient. By the way, now this is not just more convenient, in the special case that you've already gone through all of the above algebra. I mean, it certainly is more convenient having gone through all the above algebra. But let's consider what would have our alternative been if we were interested in solving these two equations. We could have said, okay, I don't want to have to deal with both of these. How about instead of doing both of these, I'll start with that equation and go through this whole process to get down to this solution, and then I just infer parts, right? So that would have been option A, is solve one complex equation. Option B is to do these one at a time, right? In which case I would have two real equations. In fact, each of these two real equations is going to have two unknowns in it, right? I'm dealing with calculus of trig instead of calculus of exponentials. Exponentials have really easy calculus, right? So roughly speaking, I would argue one easy equation instead of two harder equations. It's a lot less work, I think, to do the one above. Now, the asterisk, I have to confess, yes, there's a little bit of complex arithmetic involved in the one above. It's just not that bad, right? I think that's a very small price to pay for this very great convenience. Everybody on board with this second part? Where these come from? That comes from there. And that comes from there. Okay. All right, so I do want to show you one other thing. I talked about this in a recent lecture. How do I get it? Oh, yeah. So I talked about how you can view, for example, e to the ax cosine bx as being, there's some coefficients, and you got to think it through and find these coefficients. But that's something times e to the rx plus something else times e to the r bar x, right? And having made that observation, an integral, for example, this being a hard integral, if you do it by Calc 2 methods, right, turns into a couple of easy integrals, right? Integrals of exponentials are easy, right? And it came from making this observation that is a linear combination of that. Roughly speaking, this comes from making the observation that trig functions are linear combinations of exponentials suitably interpreted with complex numbers. Okay, so what we've got in this discussion here, let's see here, let's go to, so this business here about, making the realization that, solving one complex equation allows you instead to infer solutions to two imaginary equations. This idea, you can use that to antiderivatives as well. So that goes as follows. Let's see, where was I? I guess I was, sorry. Yeah, there we go. Another alternative of what we have above. If you're interested in the integral of e to the ax cosine bx dx, instead of playing with linear combinations like we did here, you can just make the observation that this is the real part of and just ask yourself, what is it that this is the real part of? Well, this is the real part of e to the rx. Right, so you don't even have to write it as a linear combination. You can take advantage of the fact that when you're doing differentiation and therefore anti-differentiation, real stays real, imaginary stays imaginary. And so this integrand being the real part of this integrand means this integral is the real part of this integral. Right? So again, really easy integral to do. Once you're done taking that integral, just look at the real portion. You're done. No integration by parts required. So, neat trick. Again, in my past life as a second major in physics, this comes up more than you would think. And so, being able to take what would have been a hard, integrate by parts twice problem into world's second easiest integral, right? I'll give it to polynomials. Polynomials are the easiest, right? But these are really easy integrals. Very useful. Very handy. All right. Is everybody happy? Nice trick. Okay, so we're going to move on now and talk about new material. So we're going with Chapter 4 for the moment. Moving on to Chapter 5. We're gonna define something called a linear transformation. I'll tell you what that is in a few minutes. The very first thing I want to do is get some lingo straightened out when you're talking about a function. So there are certain pieces that make up a function, and let's just make sure to get on record what are these pieces. Functions take inputs from inside of a certain set. There's this set that inputs to the function come from, and then you plug in and out come outputs. So this set that inputs to the function come from is called the domain. It's called the domain for that function. So I think y'all have heard that term before. It's pretty standard. Hopefully no issue there. Okay. Now, so there is this set that inputs come from. Now, along similar lines, there's got to be a corresponding set that outputs go into. Right? This is called the target. And the metaphor there I think is pretty reasonable. It's like this function is picking stuff up out of the domain and it's throwing it at the target. Right? So plausible terminology there. Okay, so y'all might have heard what I'm calling the target referred to with different names. Sometimes they call it the range. That's awkward for reasons that I'll talk about in a few minutes. Sometimes they call it the codomain. It's a little clunky for my tastes, right? I think target is it's a much more relatable term. So in Math 216, I'm going to be using this word target. Be aware that you'll hear it referred to differently as well. Okay. Now, this target, notice all I said about the target is that is a space that outputs from the function have to land in. What we did not say is that the outputs from the function have to fill up the entire target. Not at all. Right? The outputs from the function, well, they land wherever they land. They are whatever they are. So you might ask then, well, if I want to talk about, in fact, exactly the complete set of all of the outputs, everything that actually comes out of the function, we need to give a name to that as well. And very common choice there is image. So we talk about the image of a function. And notice the image is not the same thing as the target, right? What I've drawn here is a great example, right? The image is, what actually is coming out of this function is just that sort of smaller inside set there called B. The target's this whole purple set. Really lots of extra space there. Right, yes?
Is the target just a space, or is it a vector space?
Right now we're just talking about functions in general, and so these could be any sets of any sort. Right? We'll get down to specifically talking about linear transformations in a couple minutes. Okay. By the way, my practice is going to be to write down this number, have it on the board here until I'm comfortable that everyone's had plenty of time to get this number. So now that we've had a couple of minutes, I'm going to go ahead and lower the board all the way so that y'all in this half of the room can see the whole screen. Okay. All right. Okay. So yeah, be aware the image and the target are not the same thing. Now here's where the awkwardness comes in. Another alternative name for image that some textbooks use, range. Wait a minute. That's a word that is alternatively sometimes used to represent target. Right? So we have a problem here. This word range gets used in different contexts to refer to importantly different things. Right? So that's something to be worried about. Now, I don't have personally a very strong feeling as to which one of these is definitely right and which one of these is definitely wrong. It's just lingo, right? There's just definitions. It can be words can mean whatever people decide for them to mean. But it is very important to not confuse these objects. So my solution to this awkwardness is to just avoid the use of this term as much as I possibly can. Right? So in Math 216, I strongly encourage that you just don't use this word range because, again, in different contexts it means different things. Like, different books will define it in different ways. So I think the lingo of image and target, no problem. Let's just use those words. No confusion. Okay, is everybody on board? See what I'm talking about? Okay. All right. Okay, a couple of quick examples. Let's look at, here's a perfectly unscary function, right, from R1 to R1. So this is, by the way, this notation here, I should come back up here. When you write this, you're giving a name to the function, you're noting what the domain of the function is, and then you're noting what the target of the function is. So when you say f, x, arrow, y, you're saying that this is the domain and that's the target. Okay, so for example, perfectly unscary function takes as its input real numbers, gives as its output real numbers, and here's the formula for how to compute it. F of x is x squared. Y'all have seen this function a million times. Okay. Notice, though, the image is just the non-negative numbers, right? If you're only putting in real inputs, you will never get a negative output. Right? So the image is just the non-negative numbers. However, the target here is all of R1. Right, so this is an easy counterexample to the suggestion that image, target, same thing. No, absolutely not. Here, the image here, the target here, totally different. Okay. All right. A question that's come up. Oh yeah, go ahead.
Will the domain target always be like an R1 or R2?
Not necessarily. Oh no. Sometimes we might have the domain be maybe just the positive values of x or something like that. Yeah. So that's absolutely free. It's a free world. You can define functions on any domain with any target, just so long as all the inputs land in the output. Yeah.
So will the domain and the target always be of the same type?
Nope. Not at all. No, there is no rules. Other than that one rule is anything that comes out of the function has to land in the target. Yeah. So there's all sorts of it's a big scary world. Yeah. Totally. Okay. So a common question. Oh yeah. Go ahead. Yes. Now that's a consequence of this one rule that we were talking about, right? Anything that actually comes out of the function does have to be in the target. That's the definition of the target. And so it follows that the collection of all outputs does have to be a subset of the target also. Yep, totally. Okay, common question. Why do we even talk about targets? What's the point, right? I mean, this is exactly the set of inputs. This is exactly the set of outputs. Why don't we just talk about functions from the domain to the image and leave it at that? And this target, which is allowed to be ambiguously bigger than the image, why have it at all? Right? There's a great answer for that question, and that is it's awfully convenient. So, for example, let's look at this function here. Right? Function from R2 to R1. Very convenient to note that, look, any ordered pair of real numbers can totally go into this formula. Right? And what's going to come out? Well, this great big expression here is a real number. Okay? So it's easy to write down the domain and the target. What is not easy is to figure out exactly what the image is here. What is the image of this function? What is the actual set of outputs here? I can tell at a glance that this function can get arbitrarily large, so it's going to be, it's going to include all the big real numbers. But what's the minimum value of this function? Off the top of my head, it's not clear at all. And to be honest, depending on what you're doing, you might not even be interested in that. Why assign yourself the task of having to go through and minimize an awkward function if you don't, in fact, actually care about that, right? So the image can be a hard thing to talk about, precisely. But the target, right, giving yourself the flexibility for the target to be anything, look, just as long as we know that the outputs actually land in there, we know what category of things are coming out of this function, good enough for, let me say often. Usually. Okay, so definition of a linear transformation now. A linear transformation is a function. So domain, target, image, just like on the previous page. And there are three requirements. The first requirement is that the domain has to be a vector space. Second requirement, the target has to be a vector space. And the third requirement, the linearity condition that we've seen many times in the past, has to hold. Right? So this is just, we're finally getting around now to writing down something that we've kind of implicitly been working with already kind of a bunch, right? I mean, we made this observation that we did a lot with back in chapter 1, that if you have a matrix, you can interpret a matrix as a function. Y'all remember that? This T of x equals AX. Y'all remember that thing? And then we made the observation at some point that this behaves linearly, and we wrote down, this equation, and certain things come out of that fact. It's convenient, right? Okay, so that was an example of a linear transformation. Then we talked about determinant, and we made the observation that, well, look, if you interpret determinant a certain way, think of it as something that takes, fix everything else, but look one row at a time. Okay, one column at a time. Let's say one row at a time. Think of determinant as something that takes one of those, that takes a row vector and gives you an output value. We made the observation that determinant is always linear, one row at a time. Right? Well, linear in this sense. So that's another example of what we're now finally getting around to writing down a definition of. Chapter 4, we started talking about differential equations, this L thing, right? It's kind of a weird construction, but L is a thing that takes in functions and spits out functions. So it's a thing, it is itself a function. L is a function whose domain is the vector space of all Cn functions. The target is the vector space of all C0 functions. And L satisfies this linearity property. So that L, again, we didn't say it at the time, but it's just another example of what we're now finally getting around to generalizing. That was another linear transformation. Okay, so Several examples from our past to motivate this definition, and now we're actually making the definition. Okay. Right. Now, just some alternative ways to say this, and depending on which book you look at, you'll see different definitions of this linearity condition. This condition right here is actually entirely equivalent to this. Well, let's look at the difference between these. The top formula here says that T sort of plays nice, I like to say, with linear combinations of pairs of vectors. Right? So you can take the linear combination before you plug into the function. You can take the linear combination after you plug into the function. Makes no difference which way you do it. Specifically, linear combinations of pairs of vectors. This is saying something that at a glance appears to be stronger, namely, not only that, but T must play nice with arbitrary linear combination, any finite number of vectors. That looks different. Right? It turns out, not terribly hard to show, that any function that satisfies this condition also satisfies this condition too. So these, they look different, but they're actually equivalent conditions. So some books will define linear transformation with this formula. Doesn't matter. Yet more books will define it with this pair of conditions. Now these conditions have the advantage that they're a little easier to write down, right? This says T plays nice with addition. This says T plays nice with scalar multiplication. Each one of these formulas is arguably easier than the one up here. The downside is, of course, there's two of them. Okay. So anyway, different books, different preferences. It does not matter. They're all three of these rules that I've written down here are equivalent. Okay. Yeah. So this lingo, I like to say that a function that has this property plays nice with vector addition. I don't know. I find that sort of easily relatable, right? This is a nice property that a function would have as relates to vector addition. So another way to say that is commutes with linear combinations. You'll hear this lingo very regularly. Commutes, keep in mind, commute means that you can go in either order, right? And this is a slight abuse of the term, but it's very common. It's not a problem. The either order aspect is, well, you can add and then plug into the function, or you can plug into the function and then add. And it doesn't matter which order you go. So it's this property here is highly suggestive of the idea of commutation, and thus the lingo. Anyway, it's just lingo. No big deal. Okay, a little bit more lingo. By the way, I was asked specifically to include this discussion here by the professor that has taught Math 353, probably the most of anyone at Duke in the last few decades. So he has noticed that when he's teaching Math 353 and he says certain kinds of things, that a large number of students, more students than he wishes, don't understand what he's talking about in regards to his use of certain bits of lingo. So I want to show you some of those. So here's several examples. And these all break down in the following way, that there's something happening in all these examples that technically represents a function, but sometimes it's just kind of inconvenient to actually write that. Okay, let's give a name to this function and talk about the domain and the target, and then actually say this function is linear. Sometimes it's just more convenient to just talk about a linear process, a linear action, right? And not get bogged down with clunky terminology. So, for example, routine language. A matrix acts linearly on vectors by left multiplication. So this is a very common thing for people to say. Left multiplication, right? The action of left multiplication is that. Right, there it is. We're taking some vector x, and on its left we are multiplying by this matrix A. So that's a process. Something's happening. We call it an action, right? And we say that this is a linear process. Well, look, I could have, if I wanted to, I could have said, let's define t of x equals ax, and I could say t is a linear transformation, right? So that's fine. Another way to say it. It's just a little easier sometimes to just refer to, just look, this is a linear action. Matrices are linear. So sometimes people will say it even that succinctly. Matrices are linear. So anyway, be aware of this kind of terminology. Notice that in this case, and you're going to notice this in all of the cases I'm about to show you here, when this word linear comes up, that means that somewhere in what's being described, there is a function. There's a function hidden in whatever's being discussed. And the statement linearly means that that function representing what is happening here, that function is a linear transformation. Okay, so let's see another example. Okay, so mapping points in space to their nearest point in a given fixed plane is linear. So that's, people talk like this all the time. It's very reasonable. You give me a point, just map it down to whatever is the closest point in this fixed plane P. Okay. What that is saying is there is a function here. The function is like this, t of x equals, and then, whatever this point is. Maybe I'll call that point y. Right? So this is the function, and this function is a linear transformation. Now, that requires checking, something we have to do. I'm not going to do it here, but you can take my word for it for this example. This is a linear transformation. It's easier, though, to describe that this is a linear transformation just by saying, the act of projecting is linear, and not actually writing down a name for the function and then asserting that now named function is a linear transformation. It's easier to say this is linear. All right, does everybody see what I'm talking about? Other examples. Here's something called a linear operator. We haven't used this notation yet. We will soon. This is just the action of, when you want to do this to a function, first you take a couple of derivatives of the function, and then you take a derivative of the function and then multiply that function by negative e to the x. So that's just a notation representing the process of doing these actions to a function to get a new function. And notice, something goes in, something comes out. This process, what this operator does, is itself a function. And now, again, I could give this a name and say this thing is a function which is also a linear transformation. It's easier just to say linear operator. Okay, so again, the clue, when you see this word linear, that means that there is a process that's happening. That process should be thought of as a function, and the function is a linear transformation. Okay. Going all the way back to chapter 1, right? Way back, second day of class. We called this a linear system of equations. Now, at the time, seemed reasonable to call them linear because, all these terms, there was no quadratic terms, right? And so it's tempting to say, we call it linear because all the terms are linear. Here's a better reason to call this a linear system. This system represents the process that you might call T of taking an input vector and doing this thing that turns it into this output vector, and correspondingly writing the equation T of x equals B. Right, so this system should be thought of as, and we've done this kind of thing before, as it can be represented by this equation. Right, there's this process of turning this into that, and when I do that to some x, I get some b, and I want to solve for x. So why do we call this a linear system of equations? Well, because this thing is a linear transformation. Right, this process, this function here, of turning a vector that looks like this into a vector that looks like that, that is a linear transformation. Okay, all right, so heads up, henceforth, anytime you see the word linear, identify what the process is. Recognize that the speaker is saying that that is a function, and furthermore, that that function is a linear transformation. Okay. Okay, let's see, what do we have next? Let's see here. Yeah. Okay. This is actually going to work out. We can do this in the remaining time. I'm just going to explicitly check brute force that that's a linear transformation. I've got a function from R2 to R2. Right? Notice that there is a two-dimensional vector going in. Notice that there is a two-dimensional vector coming out. That's a vector space. That's a vector space. All that I need to check, all that remains to be checked, is that this function has the linearity property. So I just need to check that when I put a linear combination in, then I will correspondingly get a linear combination out. Okay, here we go. There's just a bunch of details in here. This vector x has coordinates. This vector x2 has coordinates. Let's just give those coordinates names. The reason I write it down by coordinates is because I know how to take linear combinations by coordinates. Right? Now, how would I plug this vector? How would I plug that into T? So how do I evaluate this? Well, we have a rule for how to evaluate this function. Whatever is the first thing goes there and there. So this goes there and there. Oh, sorry, wrong one. Here we go. There. Right, and whatever is second, namely this, is going to go there and there. And thus there and there. Okay, so all I've done here is I've used this formula to evaluate that input. Haven't really done anything yet. Okay, now this is just kind of moving things around. Again, I didn't really do anything. You'll notice that what I've done is I've gotten all the terms that have A's in them. I've kind of clumped them all over kind of to the left. And likewise, all the terms that have B's in them, I've kind of clumped them over here on the right, but I'm just moving terms around. Nothing really happened yet. And then notice that factoring out this A, like that, factoring out this B, like that, as required, that's T of x1, that's T of x2. And so it works out, right? So this is just a brute force, blunt, confirmation that this function does satisfy the linearity property. We'll talk about counterexamples next time and see a bunch more examples. All right, y'all have a good day. See you later. Have a good weekend. See you Monday.